Okay, we've had a look at the geometry of an aircraft and how we name all the various different components. What we're going to do now is move on to look at how we generate lift. And integral with the way that we generate lift is the understanding of an equation known as Bernoullis equation. Hopefully it'll be one of the few equations we use on this course, but try to understand what it's telling us, because it links the variation of speed of a flow with the pressure in the flow, and that's how we create a lift force. Now, before we move on, it's important that we just have a think about some of the laws of motion and conservation laws that we're going to use in order to carry out this discussion. Newton's three laws, very basic. What his first law says is every object in a state of uniform motion tends to remain in that state of motion unless an external force is applied to it. So if we're travelling along at a fixed speed, we need to apply a force to either speed up or slow down. And the rate at which we speed up, the rate at which we accelerate, depends on how big the force we apply to it. And also Newton's third law, for every action there is an equal and opposite reaction. So there are three laws of motion from Newton. There's a couple of other laws that we need, and these are conservation laws. The first one, first law of thermodynamics, sounds more difficult than it is. All the first law of thermodynamics tells us is energy cannot be created, nor can it be destroyed. All it can do is change its form. And finally, law of mass continuity, mass can neither be created nor destroyed. So those last two conservation laws are very important for us. So let's look at Bernoullis equation. And the way we'll look at Bernoullis equation is to begin with by considering the flow through a convergent duct. Now, our law of mass continuity says that the mass coming into that duct and the mass leaving the duct must be the same. Mass can neither be created nor can it be destroyed, and therefore mass coming in and mass going out must be the same. But because we're squeezing the flow through this duct, in order for the mass flow rate to remain the same, as the area reduces, the speed of the flow must go up. But now we have to think about the first law of thermodynamics, that the energy in the flow remains constant. Now, the energy in that flow has two forms. It has pressure energy, which we refer to as the static pressure, which is the pressure that would be felt on the surface of that duct. And it also has a form of energy, a speed energy, which is referred to as the dynamic pressure in the flow. Now, the sum of these two terms, the pressure energy and the speed energy, the static pressure and the dynamic pressure, must remain constant, because energy can neither be created nor can it be destroyed. And the sum of these two forms of energy is referred to as the total energy or total pressure, and that must remain constant. So in our flow we have a static pressure and a dynamic pressure, and the sum of those two must equal the total pressure. Now, if the flow speeds up, then the amount of energy in the speed of the flow, the dynamic pressure, increases, and therefore to maintain this balance, the static pressure in the flow must decrease. And vice versa, if we slow the flow down, then the amount of energy in that dynamic pressure will go down and the static pressure will go up, in order that the total pressure remains constant. And that's Bernoullis equation, that the total pressure in the flow is equal to the static pressure plus the dynamic pressure. So let's think about how this can create the lift on a wing. Well, here's a wing. It's a symmetric wing, and I represent the pressure on the surface by these arrows. The bigger the arrow, the higher the magnitude of the pressure. If the pressure is below atmospheric pressure, the arrow points away from the surface, and if the pressure is higher than atmospheric pressure, then the arrows point towards the surface. So what we see here is that the shape of the airfoil on the upper surface looks like that converging duct over the front of the airfoil. So as the flow comes along and sees the airfoil, it's essentially being squeezed, and therefore it must speed up, and if it speeds up, the pressure reduces and we get a low pressure, a pressure below atmospheric. As we go past the point of maximum thickness, then the flow is seeing an expansion. It's not being squeezed as much, and therefore it will slow down and the pressure will increase. So what we see is over the leading edge of the wing the pressure drops, and over the rear of the wing the pressure increases. Now at the front of the wing we see this high pressure, and what that is a stagnation point, because at the leading edge some of the flow goes over the top of the wing and some of the flow goes under the wing, but there must be one little line within the flow which doesn't go over the top and doesn't go over under the bottom, and that's known as the dividing streamline, and where that comes to rest is what's known as the stagnation point, and the velocity goes down to zero, and at that point where the velocity goes to zero we would have the total pressure, which is that high positive pressure here. But if I look at that airfoil, we see that the drop in the pressure over the top surface of the wing and the drop in the pressure over the bottom surface of the wing are the same, and so there's no pressure difference across that wing, and therefore we wouldn't generate any kind of suck in the up or downward directions, and that wing would generate no lift. It's a symmetric airfoil, it's at 0 degrees angle of attack, and it would generate no lift because the pressure distribution over the airfoil is symmetric. So how do I generate a lift force on a symmetric wing? Well, what I do is I change the angle it makes with the free stream. And if I do this, when I change the angle, or change the angle of attack, what happens now is that what the wind sees is essentially a little bit of a reduction in the area through which the fluid can travel, and therefore the flow over the top surface is being squeezed, and we can see that because the streamlines become closer together, and therefore the flow is speeding up more on the upper surface than it is on the lower surface. Now because the velocities are higher on the upper surface because the flow is squeezed more, the pressures are lower on the upper surface and there is more suck. On the lower surface the flow isn't squeezed as much, and therefore the pressure drop is not as great, and therefore when I look now I see that the pressure distribution between the upper surface and the lower surface is not the same. I get a lower pressure on the top, a slightly higher pressure on the bottom, and therefore a pressure difference across the airfoil, and the airfoil is being sucked upwards and we're generating a lift force. If I increase the angle up to say 15 degrees, what we see now is that the streamlines are much closer together on the upper surface, showing that the flow is being squeezed a lot more by the airfoil over the top surface. The velocities are higher, the pressures are lower, and over the bottom surface of the wing the flow is not being squeezed as much, and therefore the pressure drop isn't as great, and we're getting a much bigger pressure difference between the upper and lower surfaces of the wing, and therefore much bigger suck and much bigger lift force. And so what we're seeing here is that as I increase the angle of attack, the flow is being squeezed over the top surface of the wing more and more, the velocities are getting higher and higher, and therefore, according to Bernoullis' equation, the pressure is dropping more, we're getting a bigger pressure difference across the wing, and therefore we're getting more lift as we gradually increase the angle of attack. And here we've gone from -2 degrees up to about 12 and a bit degrees. If I increase the angle of attack a little bit further, what would happen? Would I still get more lift? Well, no. Strangely enough, what happens is that at some angle, if I increase the angle of attack past this given angle, the lift starts to drop. And if I look at the flow patterns when this lift starts to drop, what I see is that the flow no longer follows the upper surface of the wing. It separates off and becomes turbulent and chaotic, and the wing is said to be stalled. The lift drops and the drag goes up. So we've seen that we can generate a lift force on an airfoil by changing the pressure around the airfoil and generating a pressure difference. But now we've generated that lift force, where does it act? Well, we can calculate the lift force that we generate by taking the pressure and multiplying it by the area. And if we take the pressures around the airfoil and multiply them by the area over which they act, we can calculate the total lift force. Now, where does that lift force act? Well, much as we do with the centre of gravity, we consider the lift force to act at a point where the forces around the airfoil create no moment at that point. And this is known as the centre of pressure. Now, where does this centre of pressure sit on an airfoil? Well, it starts off at 0 degrees of angle of attack towards the trailing edge, and as we gradually increase the angle of attack, the centre of pressure moves forward towards the leading edge. And in normal cruising flight, moderate angles of attack, the centre of pressure sits at about 25% chord aft of the leading edge. As we increase the angle of attack up towards the stall, it moves towards the leading edge, and then once we reach the stall, the centre of pressure moves rapidly back towards the trailing edge.